Hi Math 30s, this is the second lesson of exponents and logs, modeling exponential functions with regression. I don't know how to, minimize that. There we go, I'm on it. This relates back to the stuff that you would have seen yesterday, looking at kind of the different values of an exponential graph and how changing them changes kind of the shape of the graph. So it goes just like with polynomials, we need to be able to determine the equation of an exponential function by performing a regression. We did regressions in polynomials, we did regressions in sinusoidal functions, same thing. So we're going to do that L1, L2, and now what we're going to do when we get to that regression screen is EXP, REG. So it's the same thing that we've done a whole bunch of times. So it says, recall, so again, this is from yesterday, exponential equations are in the form y equals a times b to the power of x. And so I'm going to try to write, anything could happen here. So a, nope. So again, a is equal to your y-intercept. And that b value, so if that b value is greater than 1, it's an increasing graph. And if b is between 0 and 1, so if b is a decimal between 0 and 1, it's going to be a decreasing graph. Oh, hang on a second. Hi, sweetie. Sorry, I have a 2-year-old. I don't know how to pause this, so you might hear him. So a decreasing graph. And again, if b is a really big value, it's going to be a really, really steep graph, whereas if b is kind of closer to 1, it's going to be less steep. So 2 questions here, or 2 different bacteria. So it says the population growth of 2 different bacteria was observed, and the results are shown below. I have literally no idea why the 4 isn't in either of these graphs or either of these tables. But what it's looking at 2 different strains of bacteria and counting what the number of that bacteria is every hour. So at time 0, there are 4 bacteria for bacteria A. At 1 hour, there are 8 bacteria. At 2 hours, there are 16. At 3, there are 32. At 4, 64. So let's even see if we can predict this last box here. So hopefully you're noticing the pattern. So from between hour 0 and hour 1, it's gone from 4 to 8. So an increase of 4, or double. And so looking at the next one, it's gone from 8 to 16. So we know that our pattern is it's doubling every hour. So if that's 64, this one would be 128 at hour 5. So bacteria B started with just 2 bacteria here, and then after 1 hour, it was at 6 bacteria. And then after 2 hours, it was at 18 bacteria. At 3 hours, 54. At 4, 162. And at 5, so what we see is between each, it's multiplied by 3. Again, this one was multiplied by 2. But between each and here, it's multiplied by 3. So 162 multiplied by 3 is 486. So what we want to do is do a regression on each of those. So take just a couple of seconds. So you can only do them one at a time. So try putting in bacteria A first into your L1 and L2. You might need to pause the video for a second because I'm not going to stop and wait. And then filling out the chart below, and then as well for bacteria B. So once you've done the regression, so again, I don't have either a TI or a Casio in front of me, but you're going to scroll until it says EXP REG. So that's exponential regression. So putting in L1 and L2 for bacteria A and bacteria B separately. So when you do the regression function, again, it gives you your A value and your B value, knowing that your form is y equals A times B to the power of x. So bacteria A should get you y equals 4 times 2 to the power of x. It says, what do you notice about the A value? We already wrote this up above. Sorry, give me a second. difficult. Um, so it says, what do you notice about the a value? We wrote it up above. So the a value is equal to your y-intercept. In the context of this particular question, it's the amount at time 0. Which again represents the y-intercept. It says, at which rate is each bacteria growing, or at what rate is each bacteria growing each hour? So it's just saying for bacteria A here. So we can see from hour to hour, it's doubling. Or multiplied by 2 each hour. So now it's asking us for the B value. So again, the B value is right here. So the B value is 2. So now you need to do the same thing, do the regression for bacteria B. So you might need to pause for a second in L1 and L2, put in those values for time and for number of bacteria. And I'll give you the equation in just a second. So when you perform the regression, y equals 2 times 3 to the power of x. So what do you notice about the a value? It's the same as we wrote there. It's the amount at time 0, which is equal to that y-intercept. At what rate is each bacteria growing each hour? So now we have, for bacteria B, we noticed it was tripling, or multiplying by 3 each time. And then if we look at the B value, again, the B value is there. The B value is equal to 3. Sorry, full screen this again. So it says, what do you notice about the B value and the rate at which the populations were growing? So it's comparing these two things. All right, well, I said doubling or multiplying by 2, the B value is 2. Tripling or multiplying by 3, B value is 3. It's the same. So just trying to apply this idea to situation F. It says, what would a B value of 1 mean in these situations? So if the B value was equal to exactly 1, so if we had something like y equals 4 times 1 to the power of x, if you put that into your equation, what you would see is a nice linear, or not a linear graph. Yep, I guess it is a linear graph. But what you would see is that there is no growth each hour. So it's not increasing, it's not decreasing. So at hour 1, there would be 4. At hour 50, there would still be 4. Okay, so that's the first little example question. So now the next one, it says examine 2 sets of data below and fill in the accompanying table. Again, why aren't these in here? Hi, sweetie. Up. Do you want to say hi? Can you say hi? Hi. Sorry, he keeps coming down. He's not supposed to. He's yelling about chocolate if you can't hear it right now. Okay, so again, it's looking at the value of a car over the course of the 4 years, I guess. So it looks like the value of the car when they purchased it at time 0 was $22,500. And then after a year, the value was $18,900. After 2 years, $15,876. So cars, they usually call it depreciation, in that it's losing value over time. Pretty much any car you get is going to do that. The millisecond you drive off the lot, you wouldn't be able to turn around and sell it back for anywhere near the price you paid, which is kind of wild. But so it's looking at the value of the car. So what we need to figure out is what's happening from one to the next, so we can figure out what the value would be at 3 years and what the value would be at 4 years. And so the way that we can look at that is we can kind of compare from 1 year to the next. So what I'm going to take is my value after 1 year 18,900, and divide it by the original value, 22,500, gets me 0.84. I hope you're double checking my math because I have that written down, but I don't have a calculator anywhere near me. So what that's saying, again, now we have an exponential graph that's decreasing, right? Because the value is not going up over time, it's decreasing over time. So looking at from 1 year to the next, there's 0.84 of the previous value remaining, or you could, if you wanted to consider it as a percentage, it has 84% of the value as it previously did. So it's losing 16% from year to year. We could also compare that here. So if we did 15,876. Hi, Callahan. All right. I know no time has passed on your end, but like 45 minutes have passed on my end. 2-year-olds, I tell you, they are people. Hopefully the first part stayed recorded. Oh my gosh, I'm going to be frustrated if it did not. Okay, so I think what I was doing is looking between year 1 and year 2. So taking the value at year 2, dividing it by the value at year 1. So give that a try, and we should get that same value of 0.84. So now to figure out in year 3 and year 4, so what I can do is I can take this number and multiply it by that 0.84 to get the value at year 3. And so I think, I can't remember if these are rounded numbers, like if they started to have decimals, but 13,336, and then same thing here, take that number and multiply it by 0.84, and we get the final value at year 4 of 11,202. So again, from 1 year to the next, it is a decreasing value, so that B value would be equal to 0.84. I guess we'll analyze this in the chart below, so I won't get ahead of myself. Same thing, so a calculator. So I'll use the TI ones because they're the more expensive ones. Yay, TI. So TIs usually, this is actually would be a really cheap TI. They're usually about 150 bucks, depends on the model. And a year later, you maybe can sell it to somebody for $118.75, and then 112, and then 107, and then 101. So it's depreciating in value. So what we wanted to see is figure out how much value is it actually losing from year to year, or how much remains, I guess, is what we're actually looking at. How much of the value remains after 1 year. So taking 118.75 divided by that original value, 125, gets me 0.95. I could do the same thing between years 1 and 2, so 112.81 divided by 118.75, that gets me 0.95. Hopefully you're punching those in your calculator and confirming that I'm not doing any sort of crazy math today. So what that's saying is 0.95 of the value remains from 1 year to the next. So 95% if you wanted to talk percentage-wise. So 95% remains, meaning it's losing 5% of its value from 1 year to the next. So doing the regression, so do the car one first. So put it in Y1 and Y2, or sorry, L1 and L2. You guys have done so many regressions, you know exactly what you're doing. And then EXP, REG, so an exponential regression, you're going to get it in the form y equals a times b to the power of x. It'll give you your a and b values though. So do it for the car, do it for the calculator, fill in a through d for both, and then unpause the video, and we'll talk about all of those things. Okay, so you've done both regressions. So, uh-oh. Why isn't it writing now? There we go. So your regression for the car, y equals 22,500 times 0.84 to the power of x. A value is, again, amount at time 0. Your initial amount, again, you could write that as your y-intercept. It says, by what percentage is the value of each item decreasing each year? So we know with the car, like 0.84 remains, or 84% remains. So the decrease is 16% per year. So it loses 16% of its value each year. And then the B value is that 0.84. For the calculator, so 0.95 to the power of x. A value is the same. It's decreasing by 5% each year. And that B value is 0.95. So it says, what do you notice about the B value and the rate at which the value is decreasing? So if we take 1 and subtract that B value, so 1 meaning 100% or the whole of it, if I take 1 and subtract that B value, so 1 subtract 0.84, that would get me 0.16, oops, which as a percentage would be 16%. So if we take 1 subtract B, that gets us our rate of decrease per year. It says if the B value was larger than 1, then what would be happening to the value of these items? And again, we talked about this before. If the B value is greater than 1, it's increasing. So in the context of kind of this question, the value of the items would be increasing. So things like cars and calculators, yeah, they're going to lose their values. Things like houses or fine art, they might appreciate, meaning they increase in value over time. All right. Okay, so the little summary page. So it says in the equation y equals a times b to the power of x. The a value is the y-intercept of the graph and is the starting point of the data. The b value represents the rate of change. So again, if b is equal to 1, there is no change. If b is greater than 1, if the data is increasing, the b value must be greater than 1. So for example, a b value of 2, so we saw that in one of our bacteria questions, a b value of 2 indicates the data is doubling each time period, and a b value of 1.15 indicates that the data is increasing by 15% each time period. So again, if b is equal to 1, it's no change. And then, like it said above, if b was equal to 2, it's doubling. So we have that b equals 1.15. So again, that 1 represents no change, but since it's more than that, since it's more than 1, it's increasing. That doesn't... by 15% overall. So that 0.15 representing 15%. So if b is between 0 and 1, a b value between 0 and 1 indicates that the data is decreasing. don't know why my E's keep disappearing. In these cases, the B value indicates the amount of data that is continuing in the pattern. So for example, so how much remains is the big thing here. Continuing the pattern, or how much remains from one time to the next time. So for example, a B value of 0.75 indicates that 75% of the data continues in the pattern, or that there is a 25% decrease each time period. So again, these numbers will add up to a 1. So a B value less than 1 is decreasing. Why won't it let me go? There we go. So again, this is our form of an exponential equation, y equals a times b to the power of x. So it gives you just what, like when we start to see some more word questions, so your initial amount or value, again, your y-intercept in that case is your a value. Your rate of change, we've talked about this. If it's greater than 1, it's growth or increase or appreciation. If it's between 0 and 1, it's decay, depreciation, decreasing. And again, to get it to percentages, you just multiply it by 100. And x, I guess we haven't really talked about it, is how many periods it is, right? If we're saying it doubles every year, then if you want 5 years from now, x would be equal to 5. So that's just kind of your general form. Hopefully all of that makes sense. And it says, given the following exponential functions, determine the starting value and the rate of change. So just boot back to this because it tells you your starting or initial value and your rate of change. So that's related to your a value and your b value. So your starting value is 100 for this first one. It's the a value. For the second one, it's 90. It's your a value. Increasing or decreasing. So again, it's based on the b value. If the b value is greater than 1, it's increasing. So 2.5 is greater than 1. If your b value is between 0 and 1, it's decreasing. So the rate of change. So, sorry, I'm just trying to figure out how I want to describe that. So 67% remains from one generation to the next is probably what we'll call it, whatever a generation is. So 33% decrease each time. And then it's, this one would be like 2.5 times as much each time. And so, yeah, I think that's it for that one. That's the end. That's it. That's all. So look at your timeline to figure out. Oh no, sorry, not look at the timeline. You guys have the questions right in your booklet. So on the next page, there's a whole bunch of questions. Just to point out one of them, on question 3, so it says the population of Canada from 1871 to 1971. If you try to put it in your calculator like that, you're gonna, I think it will work, but it might be a bit of a pain. So what I did is I called 1871 year 0, and then I called 1881, so the next one over, I called that year 10, and then 1891 year 20, 1901 year 30. So that just might help you out if you want to kind of cross those out. But just think about that your x values is years after 1871 then. So I think that's about it. Hopefully this all recorded. I'm gonna go check. Take care, guys.